Okay, so here we are with lecture 2. I'm getting PowerPoint to show within the window, so now it hasn't crashed, so that's good. So here we're going, the basic concepts we're covering here is hypothesis testing, so that refers to p-values. You may know it by its more common name like that. And also correlation, very widely used concept that it's very important to understand what it does and how it works. Okay, so in the slides we have these little animated figures which I made to illustrate some basic concepts, but the lecture notes that hopefully you have in front of you or you can look at some point really covers what we need to know for this lecture. So in the previous lecture we really dealt with the simplest case where you just collect samples of one thing that you're measuring. And let's make that slightly more complicated. Suppose you have two groups of the same thing you're measuring. So our example was you're measuring heights of some populations that you care about. In the previous lecture we just dealt with you have one fixed group, say females, and you're just sampling from the population of females, and we were concerned about error bars on the mean, for example. But now let's make it slightly complicated. Suppose you have two groups, females and males, and you're going to sample from each population, and we probably may be interested in something like are the means different? So if you're measuring heights, then almost certainly the average height of a male will be different from the average height of a female. So this is probably very much a review, but starting from the ground up to explain this. So classically, the approach you would test for differences in means is the t-test. And let's just go through the reasoning behind that kind of setup. So we want to test we're doing hypothesis testing, and we're posing the null hypothesis that the two populations that we're sampling from are actually that they're the same population. So the average, so the distribution of heights of our male population and the distribution of heights of our female population are actually the same distribution. That's our null hypothesis. We probably don't believe that to be the case, but that's what we're going to start off with. So that's the null hypothesis, and we want to basically reject that hypothesis through some statistical logic. So imagine this. So we've seen graphs like this, so hopefully I don't have to spend too long explaining it. We're going to propose this example where the red curve here is some probability distribution. The units for this don't really matter. This is actually the normal distribution, right? The mean is 0, the standard deviation is 1, and this is a probability distribution, so that's why the y-axis is p of x, just likelihood of x. And this distribution, say, is our null hypothesis. So we're going to assume that our data are being sampled from this population. And remember, we're going to have two groups, and our null hypothesis is that both groups are sampled from this one distribution. So if that were the case, then what we could do is simulate our experiment. So if we were to draw a sample from this distribution, I just illustrate that with this little, these two blue lines here. We could draw a sample of some size, could be 10 or 20 or 100 subjects. And then given the 10 or 20 or 100 numbers we have, we can compute the mean. So we might observe for some sample the mean to be maybe 0.1. Of course, it's going to be subject to variability because of the sampling. If you draw a new sample, that mean might vary a little bit. Okay, that's our first group. We collected a finite number of samples for our first group, and then suppose we collect the other group. And again, under the null, both groups are coming from the same distribution, and so that's why I'm drawing little lines from the same underlying distribution, and that's in purple here. So we draw a sample. To make it simple, just think the same number of samples, this sample size is the same across these two draws, and we can compute a mean of that. And in that case, we might observe a mean of negative 0.2. This mean we obtain will be, again, subject to variability. So we can do that, and given the data we observe, we'll compute the difference. So if I forget what I said for group 1. So the first group had a slightly positive mean, and the second group had a slightly negative mean. And we might say, aha, based on my observed data, there's a difference in this thing we're measuring. It could be height. And the difference is 0.3. So one group is 0.3 higher. The mean of one group is 0.3 higher than the mean of the other group. Okay, that's fine. And now the key point is that this whole process where we're drawing two independent samples, we're computing the means, and then we're taking the difference, that entire process is subject to this sampling error. And so on the right-hand side, we're going to look at this phrase. We used it in the last lecture. There's a sampling distribution, which just means sort of over repeated experiments, there's going to be a distribution of possible results. It's not, and the spread in that distribution is going to reflect something about the error in this process. So we're looking at the sampling distribution of this thing we just computed, the difference in the means of our two samples. So there, looks very similar to what we already had seen in the previous lecture. The x-axis is the same, the units that we're using. This could be whatever we're measuring. And the y-axis is, again, likelihood, because we're looking at a probability distribution. And so this sampling distribution, if we were to repeat our experiment 1,000 times or 10,000 times or infinitely number of times, and we plot a distribution of our results. So here I'm just putting 1x at the particular observation we had seen in our actual experiment, or at least one instance of our simulation. And then if we did this many times, we can plot a whole distribution, and we would find that it looks like this. So this distribution tells us something about the uncertainty there is, or the variability in the difference of means that we could have observed, and it tells us that values between, say, -1 and 1 are somewhat likely, that we can expect to find values somewhere between there, and then really big differences in means like 3 or -3 are very unlikely. So the basic logic is, and I guess this figure doesn't quite, okay. So the logic then is, if we like our null hypothesis, again, this is all predicated that we're, in this case, running a simulation that is based on the null hypothesis, then the logic is, if we observe something in our data that's very unlikely, then we're going to reject that null hypothesis. So specifically, if we had observed in our actual data, not all these simulations, that the difference between the means of the two groups was 1, and maybe I should have made it more extreme to make it even more unlikely, but 1 is pretty unlikely given this distribution. It's pretty far in the tails of the distribution. And so if that's the case, the further out into the tails our actual result is, then that means we have more and more evidence to reject the null hypothesis. And so a little slightly more detail, if you quantify the area of this distribution, so probability distribution sum to 1, you're always going to get some answer. But the area that's more extreme than the actual difference we observed in our experiment, that's shaded in black, that area corresponds to the p-value. So the area here might be, I don't know, 0.04. So 0.04 of this curve lies more extreme than the value we actually observed. So the logic is, we set up the null hypothesis, do some logic based on the null hypothesis. So if the null hypothesis is true, then we would expect this type of result, and then we would go look at what we actually observed in our data. And if it's pretty unlikely, then we're going to reject our null hypothesis. And let's refresh our memory. What was our null hypothesis? Our null hypothesis was that the two groups we're sampling from were coming from the same distribution. So we're going to reject that, and we're going to conclude something like, probably our two groups that we're sampling from are coming from different populations. Is this logic clear? So this is exactly what underlies like the t-test, which is sort of the parametric way to test for differences in the means of two groups based on assumptions of Gaussianity and so forth. what we're going to look at next then is sort of what's the non-parametric way to do that. So you might want to use a non-parametric way if you suspect that your data don't conform to those Gaussian assumptions, or if you want to test for something other than the mean. So the t-test classically is just the mean of your data, which makes a lot of sense if your data is Gaussian. So if you remember, if your data is Gaussian, then that distribution is summarized by the mean and the standard deviation, and it makes sense because the Gaussian is symmetric, so the mean is symmetric. But if you don't want to use the mean, or you're operating on data that's highly non-Gaussian, like it has skewness or extreme values and so forth, then you might want to use something else other than the t-test. All right. So I'm trying to multitask here, looking at the lecture notes. Okay, so let's look at some non-parametric. Oh, there was one more slide to this animation. So the p-value, I just drew an arrow to the black shaded area. So the p-value is really, again, the fraction of the distribution covered in black here. And it's on the other side because this is the issue of, you might remember, the one-tailed or two-tailed. But in this case, we're using a two-tailed test, meaning that deviations in either direction are deemed significant. Okay, so any questions on that? Or let's move on then to the non-parametric. So the first demonstration here, in case you're following along with the lecture notes, is using a randomization test, or it's also known as permutation test. And so here's a sort of illustrative example. So here's some data. The units are kind of arbitrary. This is just what I ended up using. So first, colored in red are some data points. So these are random draws from some group that we want to measure, and there's a little circle at every single data point I observe. Okay, now here's my other group. Now I plot blue circles everywhere for every data point I've drawn from this group number 2. And as you can see, there's not many data points, and it's not obvious that they're Gaussian. So maybe we might want to use some sort of non-parametric test to see if these two groups are different. By eye, they kind of look like they're different. So I'm just flipping so you can see that. So this group kind of lies around here. There's some spread, and this other group is up here and some spread. And so it looks like there may be a significant difference between these two groups. All right, so now I've just plotted a solid dot at the mean, I think. I actually don't remember. Sorry about that. Let's just say it's the mean of each sample. So the mean of all the values indicated by the hollow red circles is this right here, so about 4.5. And the mean of all the blue dots is about 4.9. Okay, so the solid red and solid blue are the empirically observed means, and it looks like they're different. Well, of course they're going to be different. It would be very surprising if they were numerically identical. But the question then is could we explain this by random variability due to sampling? That's the logic here. So what are we going to do? Well, on the right-hand side, we're going to construct something that's exactly like what we saw in the previous slide. So in the previous slide, we saw this sort of hypothetical nice example of Gaussian distributions, and you constructed the sampling distribution based on those Gaussian numbers. In this case, we're going to do exactly that, except we're going to do it computationally and based on our data directly. And so on the right-hand side, we're going to look at sort of the sampling distribution of these differences in means. Oh, they are means because I said so, means. And we're going to construct this using a randomization type technique. So randomization is referring to the procedure that we're applying, or algorithm, you could call it. Okay, so that graph is going to have values, so whatever we're measuring here, the same x-axis, and the y-axis now is frequency in actual numbers. So before we had likelihood, which is suitable for idealized distributions. Here we're actually counting results from MATLAB. So we're going to be looking at basically a histogram of our results. Okay, so we want to resample our data, specifically using randomization. And so that's what we're looking at. So the key step here is we're going to take all of our data points and throw them on one big pot, ignoring the fact that they came from different groups. And then we're going to draw groups from that pot. So the reason is, let's think back to the null hypothesis. The null hypothesis is that these two groups were actually sampling from the same distribution. So if that's the null hypothesis, then we're allowed to just dump all the data points into one pot, because that's the null hypothesis, that it's really just one pot we're picking from. It just turns out that by eye, if we look at our data, it looks like the data points are slightly different in their means, but the null hypothesis is that's just fake, that really all the data points came from the same pot. So if we dump all the data points into one pot, that's going to serve as our that's our null distribution. Like, we're using the data to construct the null distribution directly. And so if that's the null distribution, let's simulate some experiments. And to simulate an experiment, what do? We draw samples, and then we compute the mean and look at the differences and so forth. So we're going to dump all these data points into a pot and then pull out however many, whatever the sample size was here. I think it was probably 10. So we're going to pull out 10 data points from that pot, and then the remaining 10 will serve as the other group. So we're really just randomizing over a group assignment. That's all. And there's many ways to do that. So if we have 20 data points, I forget, 20 choose 10 is some big number. So there's many different possibilities. So here's one. So I'm just showing you one iteration of this simulation. I've randomly decided which data point goes to the red group, and which data point goes to the blue group. And it looks like that. That's fine. Let's compute the mean of each of these groups. Turns out the mean for the red was actually higher in this simulation. That's fine. And that difference, so we're concerned about the difference between the means of these two groups. That difference I'm going to plot. Sorry about that. That was weird. I'm going to plot that difference. So red minus blue in the units of our data is apparently 0.05. So I'm just going to put an X there. Okay, that's just one simulation. Do it again. So randomly assign our data points to group 1, group 2. Looks like that. Compute the mean of each of these randomly generated groups. Looks like that. Red minus blue is slightly negative, and it's right there. So negative 1.3 or something. And I'm just going to show you it one more time. Another iteration. Of course, we can do many more, and it's computationally pretty cheap. My power cord just died. It's not good. No, it's just disturbing because I might need a new power cord. Okay, did that one more time. Here are the means of the two groups. Red minus blue, even more negative right there. So these are just 3 iterations of our simulation. Let's do 10,000 more, or 1,000 more, however many I did. And then let's just do a histogram of all those results. And I'm just using these blue bars to show the histogram. So this looks pretty nice. It's pretty smooth looking. I ran enough simulations so that it looks like a reasonable distribution. And it shows, again, the differences in means. Each time we do a simulation, we're computing a difference in means, and we're looking at the distribution of those results that you can expect under our null hypothesis that we set up. So the null hypothesis is they were all just one big pot, and if you propose that as your hypothesis, this is what you can expect to obtain just randomly due to sampling in terms of this differences of mean. So basically it's saying if you observe anything like 0.2 difference, plus or minus 0.2, so the sign doesn't matter here. So it's saying if you observe anything within 0.2 of a discrepancy between your two groups, probably that's not sufficient evidence to reject the null, because that's highly likely. So maybe 80% of the time, I'm kind of eyeballing it, you would expect to find results about plus or minus 0.2. Whereas if you observe in your data something that's far out, like 0.6 or 0.8, that's highly unlikely given the null hypothesis. So if we eyeball our original data, so red minus blue is about negative 0.4. Actually, I think I have an animation that shows that. Oh, there you go. Yeah, negative 0.4 or something. So that actual observed difference is out here. So it's pretty far in the tails. And the corresponding p-values really just count the number of simulations less than this difference and divide by the number of simulations. And then multiply by 2 if you want it two-tailed. So two-tailed is a little conservative. It's saying I had no priors on whether I expected a positive or negative effect. I'll say any sign is fine as an effect. So you would just take that proportion down here and multiply by 2 to compensate for the other tail. Is crystal clear? Makes sense?
So is the p-value dependent on like how many times you run the simulation then? Or is it...
So question was, is the p-value dependent on the number of simulations? Technically, yes, because in this case we're empirically constructing the p-value, so you have to divide by the number of simulations you ran. But in reality, it shouldn't, as long as you run enough simulations. So if you run enough simulations, that fraction will be stable. I guess the issue with when you run these empirical simulations themselves are noisy. So if you run 1,000 simulations, you might get a p-value of 0.001, and it will be exactly 0.01 because our granularity of our simulations is 1,000, so it's going to be 1 out of 1,000 or 2 out of 1,000 and so forth. And if you were to repeat 1,000 simulations, it might go up to 0.02 or 0.002 rather. So I don't know, run 10,000 simulations and just be happy with it.
Actually, that's a good point. Do people, when they do these kind of things, do they report in terms of the granularity, the kind of stability of estimate of the p-value? Because you can place a confidence, interval over your p-value because of the number of estimates that you've calculated, right?
That's a good observation. But I've never seen any paper report. I mean, it's getting kind of crazy when you go out in the world. It's like error bars and p-values, or error bars on empirically determined p-values. I've never seen that. But you should at least report how many simulations you ran. Question?
I was just saying, when you bootstrap, you do normally report the number of simulations.
Yeah, when bootstrapping. And then in this case, I guess actually, well, yeah, when people talk about randomization tests, they often omit how many randomizations they ran. But I guess bootstrapping, people typically say we ran 1,000 bootstrap simulations, blah, blah, blah. Weird. All right. Any other questions on this? So I included, the next slide looks very similar, but I included it just because I like bootstrapping and it kind of makes sense. So the example setup is very similar. So here's some data. It might actually be the same data. So sample 10 data points from group 1, 10 data points from group 2. Here are the means. And now we're going to use a bootstrap-based method to do this hypothesis testing. So qualitatively looks very similar. Okay, so in this method, the null says all these data points are coming from one big pot. So that's just like bootstrapping in some sense. The pot is the empirical probability distribution that we're going to sample from, right? If you remember what bootstrapping is. Bootstrapping just says use your data as our estimate of what the population is and then sample from that distribution. So here, I'm going to label all the dots as gray just to indicate we actually don't care what group they are from because we're working on the null hypothesis. And now we're just going to sample from this distribution to generate the kind of experiment we just started out with. So let's draw 10 points with replacement from this distribution, like so. So here are 10 data points forming group 1, just sampling from this big pool of data points, and we're drawing with replacement because that's proper way to draw from a bootstrap distribution. And let's draw 10 more data points randomly with replacement from this big pot, and that's in blue. So what are the means of those two samples? That corresponds to something minus something, so it's slightly negative, and it's out here. That's one iteration. Let's do it again. Sample 10 data points.
Is it identical to what you just did there? What's different?
Not quite. We'll review what the difference is, but not quite. So draw another iteration, draw 10, compute the mean, take the difference. Oh, and I spared you a third iteration. So now I've done, I don't know, 10,000 iterations. Let's plot a histogram of all those results. And then let's go look what we actually observed. We observed a little less than -0.4 difference, and that's highly unlikely given the null hypothesis as we see here. So it's not quite the same. Comparing this to the previous slide, we split our data points into two groups. Sort of no point could go into the same group. We enforced that restriction, whereas here, that restriction's not really there. Here is really just saying this is the shared probability distribution across both groups. Let's just sample from it. And so this, maybe I'll just say one more thing to make it slightly more clear why you would want to go down this route. So you can run a simulation based on whatever null hypothesis distribution you want. So, and I think I give an example as the very last paragraph in the lecture notes, but you can just say, suppose my shared population was a Gaussian distribution mean 2 and standard deviation 1, something, and then you can run the simulation based on that. And so this is more in spirit of that. This is more in the spirit of what's the probability distribution, let's just sample from it. Whereas the randomization is more closely tied to the actual data points you observed and so forth. But the overall logic for sure is almost identical. Questions?
So the difference is, in one, there is you sample with replacement, and the other you sample without replacement.
So here, no, sorry, in here we're sampling with replacement.
Right. But in the other one, it's without replacement?
Yeah. But is that confusing? I mean, qualitatively, based on this example, I think the histograms look very, very similar. So if you just quickly go back to the previous
that's what I was
slide.
trying to figure out. Did anybody talk about the differences between them? Is one more sensitive than the other, or like what's the? I'm assuming if somebody's proved something about this before.
I'm not sure.
I think historically there were different approaches. Bootstrapping came later.
Oh, okay.
It's just, I think it's just a different way of thinking about the same problem. But I think bootstrapping just became popular later.
Mm-hmm. That's interesting.
What happened if you change the bin size in Bootstrap?
Change the bin
So, like-
size.
So like with bootstrapping, you're sampling like for the resample data.
Mm-hmm.
Like you're sampling n.
Yes. So in the original data that we actually acquired, let's say the sample size was 10 for each group. So definitely you need to use the same sample size in these little simulations, for the just simple reason that if you make your sample size 1,000, your sampling error would go way down, and it would just it's fine as a simulation, but it doesn't match what actually happened in your experiment. So that concern also applies to just the bootstrap in general. So if you have 100 data points, you need to draw a bootstrap sample that has size 100.
So does your bootstrap sample normally should be the same as your sample from your original data set?
Yeah, that's right. All right. So in the lecture notes, there's some other. So one point is, here we just use the mean as a metric for the central tendency of these two groups, but you can apply this identically to whatever else you want to use. So if you want to use the median, everything would be the same. You would just change the line in your code that says take the mean to take the median, and then you can run this entire simulation. Okay, so now we're switching gears to the next scenario. So this was the case of we're measuring the same thing but two different groups. So now we're going to switch to sort of the converse of that, which is you just have one group, and you're measuring two quantities from the same individuals or same subjects or same whatever. So you might measure height and weight of a group of 100 people drawn from one population. So now we have two variables. So we're instantly multivariate as opposed to univariate statistics. So what's the first thing to do when you have that type of data? According to me, you plot a scatter plot. Like that. So X could be height, Y could be weight, or it could be whatever you care about. And each red dot here is just one observation, one subject, say. Let's think of these as subjects. And here we have a lot of subjects, which is good, a lot of data. And a scatter plot is just put a dot, one dot per data point, and place the dot wherever the data values for that subject lie. So scatter plots are useful, I think, because it shows you a lot about your data that you otherwise would have almost be impossible to see as much structure as you can in a scatter plot. So anything, if you just analyze your data using whatever code you've written or someone else written, and it, will compute means and or maybe medians and so forth, that's fine, but it still doesn't tell you as much as you can learn about your data if you just look at it. So in this just one glance, you already know what the mean is of these data. You already know what the median is. You already know if there's crazy outliers or not. You already know, and you know whether these variables are related. Like you can kind of, I won't say no, but you have a very good sense of all of those things I've listed. And it's very diagnostic for weird data. So if there's problematic measurements or whatever, you can immediately see that. Whereas if you don't look at your data in a visual way, it's almost impossible to detect that. So given these two variables, I mean, this example, technically they were random draws from a normal distribution, my favorite distribution. So it's just random in MATLAB. So you can see that the bulk is within, say, 2 units from 0, and then it tapers off. And so both variables were drawn from that distribution independently. So as expected, you see almost no structure in this cloud of points. So when we look at the scatter plot, our eyes are doing the histogram for us. So remember what a histogram is. Histogram is just using bars. In the one-dimensional case, you just use bars to sort of, you count data points in bins, and then you use bars to indicate how many are in each bin. But you can apply the idea of a histogram to two-dimensional data too. And that's what this shows. So exact same axis, we're just going to bin the variables. Previously, we just had one variable, so we just bin the x-axis. Here we have two variables, so we need to bin both x and y-axes into little bins. So the bins actually are squares whose height come out of the screen. I mean, we could make a 3-dimensional bar chart, but that becomes like Excel, and those are not very useful. So let's not do that. So instead, we're going to plot the histogram using color as our third dimension. So I've binned the x and y axes into some number of bins. I just chose probably 20. And so each bin actually occupies a square in this two-dimensional representation. So for example, there's a bin that extends from 0 on the x to, I don't know, 0.25 on the x, and then in the y direction extends from negative 0.25, say, to 0. So there's just, so this one bin, the center of which I'm pointing to, it's the brightest pixel, or brightest bin. And so all we're doing is counting the number of data points that fall within that prescribed box. So very specific x value, very specific y value, count number of data points. So you go look at your scatter plot that fall there. since there are so many data points, it's very, I don't know how many, there's a lot, and it just becomes a big red dot here. So that's not very informative, but, and the actual number, I'm not plotting you a color bar. I could. White corresponds to whatever the number of data points was in here. And then darker values mean less data points were found there. So this visualization is basically telling us the same thing that the scatter plot is telling us, but they're slightly advantageous for different purposes. So, for example, on the left, this is bad for example, the peak of this distribution, you can kind of see there's a gradual peak. So there's a bright spot and it kind of tapers off, whereas our dots were so big and there are so many data points that it just looks like a solid red. So this visualization of scatter plot isn't great for discerning that aspect of your data, but on the other hand, maybe there's extreme points that were maybe very interesting. Maybe we're actually looking for data points that lie out in the extremes here, and if you do a histogram and depending on your color scheme, it may obscure that. So multiple ways of visualizing it are useful. All right, so some basic terminology here that this histogram, as we saw in the first lecture, is really just a empirically constructed probability distribution of your data. And we saw that for one variable. Here we're doing it for two variables, but it's still a probability distribution. And specifically, since there's two variables, there's some additional terms. In this case, this is a joint probability distribution. And that just means we're looking at how both variables sort of interact to give us the distribution. So I guess it's useful to look at sort of what are the other terms that we could use. So if we just did a simple histogram of the x values, so just ignore all of our y values that we measured and just look at all of our data points and what their x values are and just did a histogram, it would look like this. And I put it here just because you can just think intuitively. You take this two-dimensional image and just squash it down. So collapse all the rows together. Or in other words, you can just say sum across each column. If you sum across each column, that's basically throwing away all the y information. And we're just left with the number of data points in each of our x bins. And it would look like something like that. So that's called the marginal probability distribution. So it's sort of kind of collapsing across one of the dimensions. So this one's the marginal if we collapse away the y. So we're really just looking at x. And then this one is the marginal if we collapse across the x dimension and just look at the y values. So looking at the marginals is, of course, interesting and potentially informative, and looking at the joint distribution is for sure adds additional information beyond just what's in the marginals. And I guess the next slide will show that. So let's look at this exact same visualization, but for slightly different data. So x and y, each dot is a subject, say, and here's our scatter plot. You immediately notice interesting structure. We can summarize this data in a different type of visualization, just bin the x and y axes, count the number of observations in each bin, use a color map to sort of visualize that, and it looks like that. The histogram is effectively a probability distribution. It's a joint distribution over x and y. Let's look at the marginals, and they look like that. So if you just look at the marginals, you don't discern the correlation between these two variables, right? You have to look at either a scatter plot or a histogram of that relationship.
Is there, so in this case, you're doing a multivariate analysis between x and y.
That's right.
Dependent, and then you're pulling them apart again afterwards to get the marginal. So is there a practical application of where you would combine them and separate out the variables? Or this is just kind of, like, what is the advantage of doing this over, saying, just running two, like if you wanted to get the marginal?
Oh, yeah, sorry. Maybe I made this more complicated. I mean, the marginals are just if you just did hist in MATLAB of x, your x values. Like, you don't have to go through a joint distribution to get the marginal back again. You just, just do it directly. Just take your x values and do a histogram. this was just to illustrate the point that you can think of the marginals and the joint as being related in this fashion. So going back to the previous scatter plot, so when you see this, well, we haven't defined the word correlated, but in this case, all the data points are uncorrelated. And we'll define what correlation means, but essentially what we're saying is that the x value, or the x variable, has essentially nothing to do with the y variable. So another way to say that is, if you know that a subject has a certain x value, so suppose x value of 1, so that's where my cursor is. So if you know that some subject has x value of 1, do you have some information about his y value, his or her y value? Nope. Or another way to say that is, can you predict something about the y value if you know what the x value is? And for these data, no. And you can see that in the histogram a little more clearly, and I guess I could have plotted it, but try to see with your eye what would happen. So if we looked at let's bend the x-axis, kind of following an example I just said. So take all the data points that were between 1 and 1.25. So maybe that would be this column here. So all of the data points following my cursor here, which would be basically these data points. If you do a histogram of those data points, their y values, it would look like a normal distribution. And if you did that again for a different x value, so you go look at the histogram of the y values for x being -2, it would look essentially identical. So the distribution of y values will essentially be the same regardless of what your x value is for these data, which is just another fancier way to say that knowing x doesn't tell you anything about the y value. The y values are always distributed in this sort of normal-ish distribution. So the technical term for that is that the variables are independent. The two random variables are independent. Whereas, in this case, they're not independent. So if you know x is 2, you know the y value, or you have some certainty that the y value will be somewhat high, so maybe 1. Whereas if x is -2, you could guess that the y value is -1, say. So there is some information you learn about y if you know what the x value is. Or, in this other way, look at this sort of histogram. If you look at this slice in this vertical direction for x value of 2, so maybe that's this slice right here, and you look at the histogram of all those y values, you know that there's a big peak around here. So, okay, and we can contrast that to if x is -2. If x is -2, then you go look at the histogram of y values, and it's peaked in a very different spot. So it's peaked down here, -1 or -2. So, I guess one other way to say exactly what the same thing is that if you take the marginals and multiply them, we're asking whether the multiplication of the marginals is equal, more or less, to the joint distribution. So let's go to the easy case. So if you take these two histograms, so this histogram, and we'll do this in MATLAB actually, just to show you how easy it is to do it in MATLAB, but if you take this histogram, which is the marginal of all the x values, and this histogram, which is the marginals of the y values, and you just sort of multiply them together to fill out a matrix. So this is called the outer product, I believe, in your algebra. So if you take these two little histograms and multiply them together and fill out a matrix, you will get something that looks very similar to this little circle here. And so multiplying the two marginals is effectively generating a joint distribution that's independent across the two variables. Whereas in this case, if you take these two marginals, which if you remember from a second ago, they look almost identical to what we saw in the previous data set. If you multiply these two, you'll get a round-looking ball thing that's very unlike this. So for this data set, the actual joint distribution of these two variables does not look like what you get by taking the outer product of the marginals, which is just a fancy way to say the actual joint distribution here is not independent across the variables. There's a high level of dependency between these variables. Does that make sense? Alrighty. So, next. What's next? Okay, correlation. So I've already used the word correlation because we all use it already. But do we really know what it means? So, lead by example. So in this data set, here I've sort of omitted x and y just because we know there's x and y axis, and we're just plotting some data points. So in this kind of data set, there's a very high correlation value. So correlation's given by little r. We're talking about Pearson's product moment correlation, so it's sort of the standard version of correlation. There's some other versions. And in this data set, we compute correlation, and the correlation is 0.9. Correlation values are bounded between -1 and 1. This is probably a review for you. So this is a very high correlation. It's very close to 1. And so we can contrast some other cases. Oh, so correlations can be negative, which basically means there's a negative relationship between the two variables. So in this first case, high on x means high on y, whereas in the second case, high on x means low on y. But the strength of this relationship is the same, 0.9. And then there's also weird cases like this. So here, there's two variables, x and y. They're highly related, but if you compute correlation, it's 0. And the reason is, briefly, that this relationship's a nonlinear relationship. So a linear relationship looks like lines, whereas straight lines. Whereas in this case, it's not a straight line, it's actually a U shape. So that's sort of a warning about correlations, which we will probably pick up at some point later. But let's just stick with the linear case for now. So here down here, I'm just plotting positive relationships of different strengths. So we start out with a very strong relationship between x and y, but there's weaker ones. So this is 0.3. Sadly, people think 0.3 is a big effect, but it's pretty weak in general. And then there's 0.5 correlation and 0.7. And you can just see by eye what that means intuitively. Okay, so this metric of correlation is a number. It's summarizing all of these data, each of these individual plots in one number. So it's useful. It makes life easy. And it tells us something, which is good, but we should think about how it's actually computed and what it means. So in this slide, we have a simple example. So now I'll put the axes back on just because the numbers matter when we're talking about the details. And here are some data. So I don't know, this is probably 50 data points. And remember, these are subjects. Maybe x and y are two characteristics of each subject, and we have measurements of these characteristics for each subject. So we just plot a scatter plot just like this. And this is a bad visualization because I can't tell anything about these data given the way the axes are scaled. But I did it to illustrate a point. And the point is, when you're doing correlation, you're always z-scoring, you're implicitly z-scoring your data. And what is z-scoring? I guess we haven't defined that. Z-scoring, if you have a collection of numbers, so it's kind of a univariate thing. Take your data points, 100 numbers, compute the mean, and subtract it off, compute the standard deviation, and divide all the numbers by the standard deviation. So you're taking the numbers and just sort of relabeling the axis to be something that would be appropriate for Gaussian distribution. So Gaussian distributions are well described by mean and standard deviation. So z-scoring is like a simple scaling and shifting of your data so that the units are all well behaved. So after z-scoring, all your data points will be around 0, and they'll have nice units like 0.5 and 1, or -5, 0.5 and -1. So let me just do that to these data just to show you. So before our raw data, our actual data had these crazy units. They were all around 10 for X and 100 for Y, and they had different spreads. So on the left, the axes were specifically designed by me to be equal in metric units. So 10 pixels on the X is the same as 10 pixels on the Y in terms of these numbers. Which means that for the Y quantity has much more spread, has a spread of maybe 20, of, I don't know, 20 interquartile range if you care. Whereas for the X variable, the spread is very small, maybe it's 2. But after z-scoring each variable, so you take the X values, subtract the mean, divide by standard deviation, and you do that to the Y variables separately. So you take your Y values, subtract their mean, divide by their standard deviation. After you do that, this is the same data, just rescaled and shifted. And now it looks a little better. I'm not saying z-scoring is bad, but in this case it's very good for understanding the structure of our data. But the units are different, just something to be aware of. Notice that for along the X direction, values tend to be around 0. In fact, the mean of all the data points is guaranteed to be 0, because when you subtract off the mean of a set of data points and then compute the mean again, it will be 0. And that's true in the X direction as well as the Y direction. Also, after z-scoring, not only is the mean 0, the standard deviation of the points after z-scoring will be exactly 1. And you can see by eye that it looks roughly true. That, the average squared deviation is about 1, if by that phrase you mean standard deviation. Okay. So I'm claiming when you compute correlation, you're implicitly doing this. And furthermore, I'm going to put little dotted lines along the zeros here. So there's a dotted line on the x-axis 0 and a dotted line along the at y equals 0 over here. And now I'm going to show you what the correlation value is for these data. It's 0.65, which is pretty strong correlation. And one way to think about correlation is this value is the average product of X and Y after you z-score. So let's walk through what that means. So given this cloud of data points, some of the data points are nice, quote unquote, some are bad, right? Nice meaning they contribute to a positive correlation because that means you have a result. So, okay, what's the nicest data point? This guy right here. So this data point is 2 on the x-axis and 2.5 on the y-axis, right? So that's good. He's contributing to a positive relationship between your two quantities. So what correlation does is it takes 2, which is the x value, and takes 2.5, which is the y value, and multiplies those two numbers together. 2 times 2.5, 5. That's a big number. Good. Okay. Let's take another good data point. This guy down here. So that guy down there is -2 on the x-axis and about -2 on the y-axis. So -2 times -2 is 4. That's a big number. That's good. So we're just computing the product of the x and y coordinate in this new coordinate system. And we can do that for every single data point. So let's look at some bad data points. This guy, what's wrong with that subject? He's not really in the right spot. So he is, or she is -0.6 and on the x-axis and 0.9 on the y-axis maybe. So -0.6 times 0.9 is -0.54. That's not good. We're looking for big numbers here. So if you take the product of the x and y coordinate for each data point and then just say what's the average product across all of our data points, that'll be 0.65. So we're kind of looking for big products here. And if both coordinates are positive, that's good. And if both coordinates are negative, that's also good because negative times negative gives you positive. And the how big this value is tells you something about how well your data points conform to that kind of idea. So, in terms of some formula that just says that, so I'm going to show you one formula. There are many ways to rewrite the formula for correlation, and they're all equivalent. But one way that's in concordance to what I just described is like this. So x sub I is just the ith data point. So I is this little index that's going to vary from 1 to however many data points there are here. So we're going to subtract off the mean of all the x data points. We got to do this first step, remember, the z-scoring. So let's just take the ith data point for the x variable, subtract off the mean, which is just symbolized by that, and divide by the standard deviation of all the x data points, just using some MATLAB-y abbreviation here, STD. So this is just doing the z-scoring I just said a second ago, just a mathematical way to represent it. And we're going to do the same for the y values separately. We're going to subtract off their means, divide by their standard deviation. This now puts y into z-score units. That's fine. And then we're just going to take the product for each data point. So now we have this index, I equals 1, do that, take the product, and then go to I equals 2, do that, and so forth. And there's this big summation here, which just means every time you compute this quantity, you take the sum of all the results. That's all. And then the last bit is trivial. We just divide by the number of things we just did. Because I said a second ago, we want the average product. How do you compute the average of stuff? You sum, divide by the number of things there were. So that's all we're doing here. So I guess the main sort of intuitive point to take from this is really the z-scoring. And this is one reason why correlation, you could argue, is very useful. Because if you're relating variables that are totally on different scales, so height and weight, one's in inches or centimeters, and the other one's in pounds or kilograms. Took me a second. Those aren't comparable. Like, there's no numerical relationship between those two, so it makes sense. So you'll just say, I don't care about the mean, and actually I don't even care about the spread of each variable height, and just throw that all away and just z-score all my data. And then you can assign a number that has some intuitive meaning. 0.65 tells you that these two quantities are moderately related. Height and weight might be moderately related at this level. That's useful. Any questions?
You have a technical point. I don't know if you're going to go over it. Why use n instead of n maximum?
Yes. So the n minus 1 really comes when you're computing standard deviation as an estimate of some, and you do that n minus 1 because of unbiasedness. And here we're not really using that idea, so you don't use that minus 1. All right, so sorry if I'm going slow, but these are very fundamental basics, just to keep everyone on the same page. So there's also variance explained, this phrase I'm sure you've heard, and in the context of correlation, what you do is if you square this value, so take 0.65 and multiply it by itself, it's approximately 36.36, which means 36%. And so why would you do that? Well, if you square the R value and report, well, 36% of the variance in Y can be explained by X. So if you have a correlation, let me just say that one more time, if you have a correlation of 0.65 between variables X and Y, you can also say that 36% of the variance, which probably a big number depending on your point of view, 36% of the variance in Y can be explained by this other variable X. And it actually works both ways if we're talking about correlation. You can say 36% of the variance in X is explained by Y. And we're going to, in later lectures, we're going to go through exactly what that means, but you may have heard that phrase used before, variance explained. And again, you just square this number and you get variance explained. And remember, this possibility, you square 0, you get 0. So you don't want to say, oh yeah, x explains nothing about y. 0% explained. That's very untrue if your data look like this. And you won't know your data look like that unless you look at your data. So that's why you should look at your data. And so to deal with cases like this, I guess that's hopefully will be covered in later lectures. Remind me if I don't. Basically, how do you deal with nonlinear relationships? But I'm pretty sure we'll cover that through the concepts we go over later. All right, so moving on, unless there's questions. So this last section basically applies the same concepts that we've already went over to correlation. So the concepts of error bars, which, sampling error, there's different ways to say that, and also the concept of p-values, so testing null hypotheses and so forth. And you can apply that to whatever you want. In this case, let's think about how you might apply it to correlation. So to be a little more concrete, let's look at this plot. So down here we have a pretty weak correlation, 0.3, between x and y. And we might ask, well, might ask two questions, I guess. What's our uncertainty on the correlation? So if we were to, these are a lot of data points, so maybe I should have shown you a scatter plot with only 20 data points or something. But here, there are a lot of data points, but if we were to repeat this experiment, so sample a fresh set of subjects, measure x and y, and if we were to plot that out and compute the correlation, it's not going to be exactly 0.3. It's going to be 0.25 or 0.33 or something. So there's variability in that metric. So we can ask, how do we compute error bars or look at the sampling distribution of this thing? So that's the error bar side of it. And then we could also ask, this 0.3 on these data suggests that x and y are positively related in a linear way. It suggests, but we might ask, how do we know this is not due to chance? Which is just another way to say, let's put a p-value on this correlation. So these are two basic ideas, and we can apply it to correlation. So let's talk about, first let's talk about the error bar case. So as before, there's parametric ways to calculate error bars, which rely on certain assumptions, and there's definitely one for correlation, and you probably know that one way already. Alternatively, we can use non-parametric techniques like we've gone over for constructing error bars. So if you wanted to put an error bar on this data plot, we can use bootstrapping. So let's go through the logic. We're going to use the data points we observe here. So these are the actual data points, and treat that as the underlying population that we're sampling from. All right, so we're just going to take those data points as is, and now we're going to construct, basically simulate an experiment, draw a random sample of the same size that we've actually used for our experiment from those data points with replacement. Exactly the same idea in the one-dimensional case. In the one-dimensional case, we have 20 numbers. We're just going to say, let's draw 20 numbers with replacement from those 20 numbers. Here, we actually have, let's say, 100 subjects and 2 numbers for each subject. So there's 200 numbers, but no big deal. It's the same underlying idea. We have these data points. Let's draw with replacement from these data points. Okay? So we draw a sample, and then compute the correlation you observe in that sample. And then draw another sample, compute the correlation. Draw another sample, compute the correlation, and do that, say it 1,000 times. And then immediately we look at, we see the uncertainty in the correlation values. We'll see you can plot a histogram of all those results. And so the logic is identical to what we already covered. And we'll go through again, how do you actually do this in MATLAB? We'll go over that, but conceptually, nothing new is happening here. Okay, so the error bars are bootstrapping to derive an error bar based on for the correlation is pretty straightforward. Let's think about the p-value here, or testing the null hypothesis. So first, let's just think about what is the null hypothesis we're trying to test for these data. So we have x and y. We think that there's some relationship between x and y. But let's pose the null hypothesis that we're trying to reject in some sense. So the null hypothesis is that, I guess, intuitively speaking, there's no relationship between x and y. So pick your favorite two variables you think about. So I don't know, people's color preferences and people's height. There's probably no relationship between those two things. So that's our null hypothesis, that there's no relationship between x and y. And given that null hypothesis, we're going to do some non-parametric resampling based on that. So specifically, if the null hypothesis is true, then there's nothing specific about this particular ordering of x and y values. We can essentially shuffle all the x values around randomly. And while we're at it, we might as well shuffle the y values. Let's just shuffle which subjects are assigned which x values and which subjects assign y values. So in our actual data set, each subject has a specific x and y value, but let's just break that relationship. Let's just say we can randomly reassign all the x values across our subjects. And that's consistent with the null hypothesis. Null hypothesis says there's no relationship, so it doesn't matter. We can just shuffle as many times as we want. So we'll just shuffle all our x values and then compute a correlation. And then shuffle again, compute a correlation. Shuffle again, compute a correlation. And as usual, we'll get a sampling distribution, we'll get a random distribution, like something that looks like that. And then we'll just look, what is the actual correlation we see in our data set? Is it pretty far in the tails? And that gives you your p-value. All right, so maybe I'll stop